This is the first in a series of 2 videos in which we explain how to calculate the titration curve of a weak acid with a strong base. In our example, we're going to use acetic acid, only 20 mL in a concentration of 0.1 molar, and then we're going to titrate that acetic acid with sodium hydroxide with concentration 0.1 molar. Now, we're going to be calculating the pH for various additions of the base. Okay, we're going to calculate the pH at no base addition at the start of the titration, and then as we add 10, 20, and 20.5 milliliters. In this example, we're only going to see 2 of these points, the initial point and then the equivalence point. And then in the second video, we will take a look at the other cases. All right, let's first write what the reaction at hand will be. All right, the reaction is acetic acid reacting with sodium hydroxide to generate sodium acetate and water. All right, great. So let's go to the first point where we only have the acid. Now, something that is very important about this problem is that this is a weak acid, and what that means is that it's not fully dissociated. Instead, acetic acid has an equilibrium characterized by an acid dissociation constant that is quite small. Okay, so if we write that equilibrium here, that will be as follows. Acetic acid, protons, and then acetate, both of which would be in aqueous solution as well. All right, so this is a weak acid. The acid dissociation constant for this acid is 1.8 10 to the minus 5. And what that means is that this equilibrium is very displaced towards reagents. Right, so in order to calculate the pH at the start of the reaction when there's only weak acid present, then what you have to do is run an ice diagram, calculate the concentration of protons at equilibrium from there, and then that will give you the pH. All right, so these are those calculations, even though we have explained in prior videos how to do this reasonably well. All right, so in your ice diagram, you simply write your initial concentrations, which for this case is for 100 molar, 0 and 0, then the change. The reaction will be to produce protons, X and X, and then at equilibrium you will have 0.100 minus X, X, and then X. With the equilibrium values, you go to the equilibrium constant, which is simply the concentration of protons plus the concentration of acetate over the concentration of the weak acid. And then notice that this is going to be equal to X squared over 0.100 molar minus X, and that has to be equal to the equilibrium constant, 1.8 10 to the minus 5. Okay, so that is a quadratic expression that you can solve using approximations or an iteration method or the quadratic formula. And the result that you get out of this is that X, which is exactly the same as the concentration of protons, that value is 1.3 10 to the minus 3 molar. All right, so now we're ready here to take the minus based on logarithm of that number to obtain the pH. And when we do, we find that pH is 2.87. Now, in a prior video, we have calculated what the pH would be for a strong acid in the same concentration, 0.1 molar. For example, consider hydrochloric acid. That first calculation gave you a pH of 1. All right, so you already have that the titration curve of a strong acid is quite different from a weak acid if they have the same initial concentration. And that is due to the strength of the acid, right? A weak acid is going to give you a much higher pH than a strong acid. All right, so we're done with our first point in the pH curve, the titration curve. Okay, and now we're going to head now to the equivalence point, which will be also quite interesting and different from what happens with a strong acid. All right, so let's go to the equivalence point. And that is the situation in which you have added the same number of moles of acid as you have of base. All right, so we're going to go here to this reaction and then write the number of moles before reaction and then after reaction. Right, so initially we have 20 mL of 0.1 molar of the acid. That means that you have 2.00 10 to the minus 3 moles of base. You add 2.00 10 to the minus 3 moles, because that's 20 mils, 0.1 molar, and then you initially don't have any acetate. Well, this is the chemometric reaction, so there's no acid or base left. You have zero of this, zero of that, but here's something that is quite important. You have now generated 2.00 moles of acetate. And this is important because acetate is the conjugate base of a weak acid. And as such, it will have acid-base properties, right? The pH will be basic because this ion, the acetate ion, is a conjugate base. Right? So we are no longer going to expect the pH to be 7, as is the case for for a strong acid titration. Now the pH at the equivalence point will be basic. And again, that is solely due to the acid-base properties of the conjugate base of the weak acid that we're titrating. Right, so let's think a little bit about that acid-base properties of the conjugate base. Notice that you're going to have acetate, and in water, there is an equilibrium that produces acetic acid and hydroxide. Right? So the presence of that hydroxide produced during the reaction will make the pH of the solution basic. The only thing that we have to do is then calculate what the concentration of hydroxide is at equilibrium, and then that will give us the pOH, which we can turn conveniently into the pH. And the way to do this is by simply engaging here another ice diagram, this case for the conjugate base. Alright, so this is your initial change and equilibrium concentrations. Here we have that the initial concentration would be as follows. Notice you have 2.00 10 to the minus 3 mole. You have to divide this over the volume. And the volume is the 20 mils that you had initially of the acid, plus the 20 mils that you have of the added base. So the total volume of this is 0.040 liters. Right, so from that you get a concentration for this ice diagram, which is 0.0500 molar. And we assume that because all of the acid has been consumed in the reaction initially, before acetate starts to do its acid-base chemistry, that concentration will be 0. And initially we also assume that the OH concentration is 0. Then the change will be reaction of acetate with water to generate hydroxide, X and X, and at equilibrium you will have 0.0500 molar minus X, and then X and X. Right, so from here we have to go into the equilibrium expression and then figure out what that equilibrium constant is and how to solve for X. Now remember that this is now the conjugate base of a weak acid, right? So let me see where I can write here the equilibrium constant. Okay, so B is going to be equal to the concentration of acetic acid times the concentration of hydroxide over the concentration of the conjugate base, which from our ice diagram is 8x squared over 0.05 minus x. And the value of this K sub B is simply the auto-ionization constant for water divided over the K sub A of the acid. That's how we calculate the equilibrium constants of conjugate bases. And this is something that we have already explained in a video. And just plugging here this value of the K sub A and then taking 1 10 to the minus 14 for water, you get a value of that K sub B equal to 5.6 10 to the minus 10. All right, so you're back at your algebraic calculations where you will have a quadratic expression which you can solve using an approximation here, and that is to neglect this x with respect to this number. And then what that returns is x, which happens to be the concentration of hydroxide. This is important. Don't confuse this with the concentration of protons. Notice that this is a base equilibrium, so your product is hydroxide, not protons. The concentration of hydroxide here is going to be 5.3 10 to the minus 6 molar. From here, you can take the minus based on logarithm of that number to generate the pOH. And this is equal to 5.28. And finally, you subtract that number from the pH, from 14, and that will give you the pH. Okay, so that minus 14 minus that number happens to be 8.72. Right, so here we have our second point in the titration curve. That is the equivalence point, which in this particular case is not pH, neutral pH, right? Notice that because you have now a conjugate base with sizable base properties at equilibrium, then that pH will be basic, and this is a significant difference with respect to a titration of a strong acid with a strong base. Right, so in this video we have started to see how to trace the titration curve of a weak acid with a strong base. We have looked at only 2 points. The initial point, and for that we have engaged an ice diagram of the weak acid, and then the equivalence point, which requires an ice diagram of the conjugate base. In the next video we're going to finish this titration curve by looking at what happens at these 2 points. A point right after you have passed the equivalence point and just add half mil more of the base, and then a point where you have added 10 mils of the base, which will be half equivalent of the weak acid.